Hello, everyone. Welcome back. So today we're going to be continuing our journey through acid-base chemistry by approaching equilibria in acid-base chemistry. And so we talked a little bit about equilibrium already, right? We had an example in the past. This is when we were looking at the energy diagrams of mixing HCl and H2O. And of course, we've seen this reaction many times. It makes H3O plus and Cl minus. But we did say earlier that there's a value for the equilibrium constant for this reaction. And we said that it was 10 to the fifth. And we were using this value right here to justify the way that we've drawn an energy diagram. But the question becomes, where do we get this value? So where does this come from? Right? And that is the basis of today's lecture. We're going to be talking a little bit about how we're going to come to conclusions about equilibrium, and we're going to start to calculate a little bit about equilibrium constants. But the most important part is we're going to determine whether or not something is favorable for an acid-base reaction. And so where this KEQ value actually comes from is through something called an acid dissociation constant. And this is one that you may remember from Gen Chem. It is Ka, and we will also be using pKa. And so the acid dissociation constant is very simple. The general way we can put it is if you put an acid, right? So Ha, where A is the acid and H is the proton that's being deprotonated. If you toss that into water, a reaction should occur, right? An equilibrium reaction in which you generate H3O plus and whatever that acid is now with a negative charge. And so this equilibrium constant is the acid dissociation constant. But the way this actually works is that essentially, we've talked about a little bit in the past that KEQ, right, which is our equilibrium constant, is the concentration of products over the concentration of reactants. But the thing with Ka is that it makes one major assumption, right? Because if we look at KEQ for this equation here, we would say that the products are H3O plus and A minus, but the reactants, on the other hand, are the acid itself and water. But here's the thing, for this reaction specifically, it is run in water. So what they do whenever they run these is they keep water a constant concentration, right? And it's also very large concentration in comparison to everything else. And so to determine Ka, what we do instead is we then multiply this by the concentration of H2O because it is a constant. And if we multiply both sides by the concentration of H2O, you can imagine this is going to cancel out on this side. And now it's KEQ times the concentration of H2O equals all of this stuff. And this is actually the definition of Ka. Because Ka is the concentration of the generated um, hydronium times the dissociated acid over Ha. And here's the thing, right? This entire equation right here, the whole point of it is it measures the strength of an acid. And the way it does that is you can imagine the more acidic something is, the more of these top two things that it makes, right? Because the more acidic, the more H3O plus it's going to make because it's going to protonate more things. And so essentially, these Ka values tell us exactly how strong an acid technically is, especially in comparison to water. And so with these Ka values, the thing is, these will always come out to be very wonky. So what people do instead is they actually take the negative log of the Ka, and this gives a value that is the pKa. All right. And the pKa, this is going to be our friend, right? This is what we will use to truly determine acid strength. and somewhat also base strength. So here's the thing, right? This is a lot of math. Essentially, if you wanted to do this, you'd have to sit here and do experiments where you toss these acids into water and you see what they actually make. But thankfully, people have done this quite a bit. And so they've come up with some tables that have a bunch of pKa values in them. And what we're going to use for this class specifically is this nice pKa table here by Dr. Noel Paul. Shout outs to him. And he calls it the Lucky 13. And what the Lucky 13 is, if we zoom in a little bit, it is essentially a list of pKa's for different things that span a giant range. All right. And so the first thing that you need to know about pKa's is the lower the number is, the more acidic something is. Right. So, oh, I gotta change my pen size here. So a lower value equals more acidic. And so if you think about why this is the case, the Ka will grow larger as we make more of the products, right? Because it is products over reactants. And if we look back up at this here, right, the more H3O plus and A minus we make, the higher that Ka value is going to be. But whenever you take the negative log of it, you're essentially doing 10 to the negative of that value. So the lower value means that we're looking at something more acidic. So that brings us to this first column right here that we can take a look at. Right, and the nice thing about this pKa table that we have is it describes a lot of things for us. The first thing it does is it tells you the name of the functional group and its pKa. All right, and so if we're looking at lower values that are more acidic, essentially what we're saying is those acids are able to dissociate easily, right? And that's what's in the second box here. It just says that these are strong acids. All right, and it also tells us down here that these are weak bases because they have stable conjugate acid or conjugate bases, I suppose. And so the other nice thing that it does is it shows the functional group with the proton attached. So that would be right here in the middle with the HX, and it shows you what the conjugate base actually looks like. All right. And then the very, very most important thing is right here at the bottom, which is what we're going to be using a lot of, and that is these stability effects here. All right. And it tells you why these things are so acidic. And so these 13 functional groups, I would say, are very important to at least know within the ballpark of where they sit. And the reason is because it's going to become very nice and easy for us to use these as reference points. And they're not entirely, you have to know them specifically, but it is nice to have something to reference whenever we're looking at equilibrium in these reactions. So we're just going to go through and we're going to talk about each of these different acids, and we're going to see why or why not they are acidic. So, looking at the next one, oxonium, right? This is our friend H3O plus, essentially, and it sits at a pKa value of 0. And it is acidic because of primarily the fact that the oxygen is electronegative, and if you deprotonate it, it becomes a neutral charge. All right, the next up, and by the way, this is the line right here where we would separate things that we would call strong acids, right? Whenever we described before, all of our inorganic acids like HCl, HBr, HI, H2SO4, right? All of those fit into that range of about -5. Then H3O plus is right around 0. Everything above those values is where we start to get to the middle range of acidity, right? So these are the things I would start saying you should probably think about whenever you're looking at acidic protons. So something like a carboxylic acid, right, which is that really fun functional group that you've all seen before, has a pKa of right around 5. All right. Ammonium, which is a positively charged nitrogen. So notice we had a positively charged oxygen at 0, and now we have the positively charged nitrogen. It is at 10. So the difference between these two groups is 10 pKa units. And we'll talk about what that actually means in a second whenever we look at how these pKa's measure acidity. But keep in mind that this is on a log scale. So it increases much faster than you would actually expect. Now then, next one up is dicarbonyls. So this is a group that we haven't looked at very much yet, but it's very important because if you take a look at the acid and conjugate acid, you can see that the carbon with the negative charge has resonance with both oxygens beside it, right? It can do resonance in either direction. And because of that, it actually has a relatively mid to low pKa right around 10. Next up is alcohols, right? So whenever you see any of those OHs, those hydroxyls, those have a pKa right around 15. And this is about the area that I would say is this is sort of the middle in terms of acidity, right? So they're relatively acidic, but they're also not super acidic. Next up, we have carbonyls. So unlike the dicarbonyl, where it has resonance with two oxygens, this one has resonance with a single one, and because of that, it makes it somewhat acidic, but not very. Looking a little further past this is when we start to get to the range of things that are not very acidic, right? And especially if we draw another line, actually, we'll be even nicer and draw the line right here. This is when we start to get into things where we're looking at weak or very weak acids. All right. So we have alkynes at right around 25. And then these diallyl dibenzyl, which are essentially just carbons with resonance to other carbons. We have amines. So notice how whenever we talked about electronegativity in the past and we looked at alcohols and amines, notice that alcohols sit at 15, amines sit at 35, right? So neutral nitrogen is a bad acid, right? It's a very bad acid, unless it has other effects to go along with it. That being said, the rest of these are carbon-containing acids. You have allyl benzyl, which are just carbons with resonance, alkenes, so just sp2 hybridized carbons, and then finally alkanes, which are sp3 hybridized carbons. And this right here is by far the weakest acid. But one thing that you may notice is also written on here, which we talked about right at the very beginning, but we didn't go too deep into, is base stability, right? Because even though we're moving from a lower value of pKa, which is more acidic, if we move all the way to these high value of pKa's and we look at those conjugate bases, such as this one right here, this is the strongest base that's associated with this. All right. And so essentially, as we move down this line, we can see that some of these things become they're pretty good bases, but they become less basic as we go along, right? Because the weakest bases are the strongest acids. So something like this X minus, which is normally just a halogen with a negative charge, it's a very bad base. But as we move up, we see that things like negatively charged oxygens, right? So think sodium hydroxide. This is actually in the middle of bases, right? So this is a another mid-strength base. So last lecture, whenever I called it a strong quote unquote base, it was strong whenever we thought of it in terms of gin chem, right? But now we have a whole other scale to work with because all of these things over here are much, much stronger bases than a O minus, right? And so something that I would like everyone to keep in mind is that this chart not only tells us what is acidic, but it also tells us what is basic. All right. So what I want you to glean from this chart whenever you look at it is first of all, start to kind of get an idea of what these pKa's are and what the ranges that they sit in are. They're all within increments of 5, so it's pretty easy to keep in mind. But then the other thing that we want to pay attention to is, as I said before, a lower pKa means that it is more acidic, right? Because it's less stable. But that does mean it is a more stable conjugate base, right? And what we can say from our knowledge of conjugate bases is if something is stable, right, such as a stable conjugate base, that also means it is a weak base. Same thing can be said on the other end of the scale. A higher pKa means that it is less acidic, right? It also means that it has an unstable conjugate base. And as we know, an unstable conjugate base is a strong base. All right. So I will be pulling from this pKa table as we go along. So I would recommend pulling up the one that is on Canvas so that you can kind of follow along with where I'm gleaning values from as we go. But I'm going to use some of these values to make some arguments as we go along. And the first thing that we're going to talk about is thinking about the acidity in terms of its power, which is a really weird way to say this, but it'll make sense in just a second. So let's say that we were comparing the acidity of ethanol versus ethylamine, right? Looking at this, these are two different compounds that are found in that pKa table up there. So for the alcohol over here, the pKa is about 15. For the amine, the pKa is about 35. So if we asked which one is more acidic, the first thing you should think of is, well, the alcohol has the lower pKa, therefore it is more acidic, right? We can also use the things that we learned from last lecture, right, where we talked about electronegativity being a big factor in acidity, and we can say that an oxygen with a negative charge is more stable than a nitrogen with a negative charge, therefore the OH is more acidic. All right? So both of those arguments are important. But the thing that you need to remember is knowing the arguments from last lecture is more important than just being able to say pKa is lower. All right? But what the pKa tells us here, right? Because we know either way that the alcohol is more acidic. But the question becomes how much more acidic is it? And so that's where this idea of the power comes into play. Because the difference in pKa is 20, right? So it's just simply pKa difference is 35 minus 15, which is 20. And so you may think to yourself, it is 20 times more acidic, right? But the thing is, that's not actually how the pKa scale works, right? Because remember that when we're talking about pKa's, it is the negative log of the Ka, right? And so if you do some conversions, what you'll find is that the negative or the Ka is 10 to the negative pKa. And so what that means is that this is, instead of just being 20 times more acidic, it is 10 to the 20th times more acidic. And that is a unfathomable number in terms of strength, right? And again, you don't need to know all of the math behind this, right? You just need to know that this is just a good way of thinking about this acidity. So even a single pKa unit is 10 times different from the other, right? Another one that we can look at is, let's say that we were doing a similar comparison with this carboxylic acid versus the same alcohol, right? For this here, we already know that the carboxylic acid is more acidic because upon deprotonation, it's a negatively charged oxygen that can share via resonance to the other oxygen. But using a pKa value, we can find out how much more acidic it is. Right, so a carboxylic acid has a pKa of 5. We just described that this alcohol has a pKa of about 15. And so we know this is more acidic, and so 15 minus 5 is 10. So this is 10 to the 10 times more acidic. So it's a very large amount more acidic. And now where this matters is how it relates to our KEQ, right? Because whenever we take a look at our KEQ, right, we can take a look at the relationship here. So one equation that I will say is useful that I will give you and that you kind of need to know is that the KEQ is always going to be 10 to the pKa of the conjugate acid minus the pKa of the acid. All right. So we're gonna take a quick second to put this into practice to show us how this KEQ idea works. All right. So let's do our favorite reaction once again. I know I keep showing it, but it's a good example reaction to work off of because we do already know the KEQ of this reaction, but we're going to demonstrate how you can actually find it given the pKa values that we have. So what we need to know for our KEQ is we need to know the pKa of the conjugate acid and the pKa of the acid. So first we have to identify those, right? We know that HCl is our acid on this side. On the other side, remember that our good old base, which is water, is what's going to make our conjugate acid, in which case the acid will make the conjugate base, which is the chloride. So we have our acid, we have our conjugate acid. And if we look at the pKa table, we can find that the pKa of HCl, it's one of those inorganic acids. It's about, sorry, not 5, it's about -5. And then the pKa of hydronium is right around 0. Okay? So if we wanted to find the KEQ of this reaction, we would say that KEQ equals 10 to the, and it is the pKa of the conjugate acid, which in this case is 0, minus the pKa of the acid, which is -5. Minus and minus makes a plus, so our KEQ for this reaction is 10 to the 5th, right? And whenever we're thinking about what direction that points, as a reminder, since our KEQ is much greater than 1, the products are favored. So essentially what we can do is we can start to identify when acid-base reactions are going to go in a direction and how strongly they're going to point in that direction. So what we can actually do is we can go ahead and we can do an example, right? And this will be our first example of a real acid-base reaction that we need to think about. Okay? So let's do something like this. All right. So for this reaction, I'm just going to give the reactant and the product so that we can do it rather quickly, and then we'll move on to some where we have to start using our brains a little more. So for this reaction, we have a carboxylic acid and an alkoxide making a carboxylate and an alcohol. So first things first, whenever I look at this reaction, I see a negative charge on that oxygen. That immediately tells me this is the base, right? That also tells me that this is the acid. And when we look at this acid, we have to identify where the most acidic proton is, right? And we know for a fact that it is this one here, right? Because it's connected to an electronegative atom. And once that oxygen has a negative charge, it'll have resonance with the other oxygen. So this makes the most sense to be the most acidic proton because the only other protons that are present that could be it are on this carbon over here. And remember, carbon is not particularly happy losing a proton. So if that's the acid, that's the base. That tells us that this is our conjugate base, and this is our conjugate acid. So if we wanted to determine the exact KEQ value of this reaction, what we would do is we would say, all right, we need the pKa of the acid and the pKa of the conjugate acid. So for our acid, this is one that's in our pKa table. It's right around 5, right? This is the exact same as we were looking at before, where this is our carboxylic acid, and then our alcohol is right around 15. So then where we want our KEQ, what we would do is we would do 10 to the, and it's conjugate acid, which is 15, minus 5 for the acid. And that tells us that the reaction has a KEQ of 10 to the 10th, right? Once again, products are favored. which is great. So this is an example of how we can use these pKa values to kind of justify an equilibrium constant value. Okay? But here's the thing. We don't always have a KEQ value, right? That's only 13 different values. So we have a slight problem, right? Sometimes we need to make some educated guesses to determine which direction something is going to be. All right, so you can use the pKa table to make educated guesses. So we're going to show an example of how this is done. And the way we're going to do this is we're going to take a look at a reaction here, which involves a alcohol and a sulfide, making an alkoxide and a thiol, like this. So, looking at this reaction, once again, I see on the left-hand side we have a base. All right. And then that does mean that the alcohol would have to be our acid, right? And we know that based on electronegativity, that would be our most acidic proton. But with that being said, this would be our conjugate base, and this would be our conjugate acid. So, if we wanted to determine the equilibrium constant here, right? Looking at our acid, we do know this one's pKa, right? It's one that we've seen multiple times. It's right around 15. But over here for our conjugate acid, we have a problem because we don't have that pKa in the table, right? And if it is not in the table, that means that we have a little bit of a problem. We have to determine the equilibrium based on effects and determining whether or not something should be more or less acidic. So, how would we determine which one of these is a better acid? Well, to do so, we would use the information from last lecture, right? And what we would do is we would compare the base stabilities, right? Because remember, when we're talking about acid-base chemistry, it is a stronger acid makes a more stable base. So the two bases that we have shown are our base and our conjugate base. And we're essentially asking which one is going to be more stable. And well, if you remember back to last lecture, it would be this one on the left, right? Because size, right? Bigger is better. And so since sulfur is larger than oxygen, this is the more stable base. So if this is the more stable base, right? More stable base means that it comes from a stronger acid. So that tells us that whenever we take a look back up here at our conjugate acid, and the pKa is something that we don't know, we can actually say pretty definitively the pKa is less than 15, right? Because remember that a lower pKa is a stronger acid, and we've already defined the alcohol as having an acidity where the pKa is 15. So it's got to be lower than that. So what that tells us is if the pKa here is less than 15, the pKa over there is 15, that tells us that our KEQ has to be less than 1, right? And the reason we come to that conclusion is because you can imagine that even if this was 14, for example, that would be 10 to the 14 minus 15, which would be 10 to the negative 1, and 10 to the negative 1 is less than 1. Okay? So, with that being said, that's a way that you can think about this. And it tells us that our equilibrium is reactants that are favored. All right? And this is a fine way to think about it. The other way that you can think about this is you can say to yourself, the equilibrium actually always points away from the strongest acid, right? So what that would mean is no matter what, equilibrium is pointing away from the SH, right? Notice how this is true for everything else we've talked about so far as well, right? The other ones we had definitive numbers to kind of track exactly what we were doing. This one, we're just making an educated guess and stating that the KEQ is less than 1, but we don't know exactly what it is. Looking up here, the same trend holds, right? The stronger acid in this pair was the carboxylic acid, right? And the equilibrium pointed away from it, right? It was a product favored equilibrium. Same thing up here, right? HCl is a stronger acid than H3O plus, and our equilibrium pointed away from it. So even if you don't know exact values, you can tell which direction the equilibrium is pointing based on which side is going to be more stable, which is always pointing away from the stronger, unstable acid. All right? So, thinking about that, we can make these educated guesses, and a lot of the times you're going to be pretty spot on, but of course you won't know the exact values. I will say for this one, what we decided was a good idea because the pKa of this SH is actually right around 10. All right, so essentially it would be a 10 to the negative fifth, which does point the equilibrium even further over towards the left, but we didn't know that directly from numbers. We could just make that assumption. Okay. So that's what you do if a pKa isn't in the table. And so we're going to go through and we're going to do one more example of this idea before we move on and we talk about how this is going to look on our quizzes and exams. So let's do a second example. Sorry, is this example three? I don't know. I guess it's example two. Right? Let's say that we were looking at the following reaction. All right. So for this one here, we start out with a negative charge on this side, which tells us immediately that this must be the base. And then we see that this must be the acid. Great. Then we look on the other side and we see that that means that this is the conjugate base. That means that this is the conjugate acid. And once again, we find ourselves in a position where not both of the pKa's are in the table, right? The conjugate acids it has a pKa of right around 5. It's carboxylic acid. But the other one is not. But the funny thing is, it's also a carboxylic acid. But the thing is, this one can be affected by the other factors that are related to it, right? Looking at this carboxylic acid over here, we see that there is 3 fluorines hanging out on this side of the molecule. Whenever I see that, the first thing that I think about is, hey, this is probably induction. Because if you remember from the previous lecture, all those fluorines are pulling dipoles. And what that means is whenever we look at our product, there's a pretty big dipole being pulled in the direction of the fluorines, which means there's more of a partial plus over here, more of a partial minus there. And that would tell us that our conjugate base is stabilized via induction, right? And if this is a more stable conjugate base because it's sort of putting a partial positive charge on the negatively charged oxygen, that means that the acid must be stronger. So if we're looking at the pKa of this acid, it would be less than 5, right? And so if this is the stronger acid, equilibrium is going to point away from it. That means the equilibrium is in this direction, aka our KEQ is greater than 1. So remember that when you're looking at these pKa's, they're very useful, but you do need to take into account the fact that it's not going to always be exactly what's in the table, and you need to pay attention to make sure that there's no other factors that are influencing your acidity. So with that being said, let's take a look at what this will look like on your quizzes and exams, right? So on quizzes and exams, you will be given a 3-part question, right? The first part of the question is to predict the product of an acid-base reaction. Right? Sorry, I shouldn't write it as RXN. Should write it as the full name reaction. So this is essentially saying you're going to be given some reactants. You're going to have to tell me what the product is. The second thing you're going to have to do then is you're going to have to determine the direction of equilibrium. Right? So just like we've been doing with these previous ones, you're going to have to tell me which direction equilibrium is pointing. And the part that is even more fun is you'll have to say why, right? You'll have to give one reason. So we're going to go through a bunch of examples of this because I think the only way to understand this is to practice it. And so we will start out with example number one of a problem that you may be given on a quiz or exam. So let's say you were given this here. This is all you would be given. And you would have to determine from this here exactly what is going on. So, first thing we got to do is we have to predict the product of the reaction. To do this, I recommend step one is you always need to identify your acid and you always need to identify your base. So looking at these two structures, the first thing that I personally notice is a sodium, right? And what a sodium tells me is that this sodium is just going to be a bystander, right? It's a spectator ion. It's not going to do anything. And if the sodium is positively charged, I look over here and I see this nitrogen, right? It definitely has some lone pairs. It is negatively charged. And since it's negatively charged, that immediately hints me into the fact that this must be our base, right? Because things with negative charges are generally bases. That then tells me that this here is our acid. So now what we need to do is we need to determine next what is our most acidic proton. So looking at our acid, right, finding our acidic proton here is generally pretty simple because we have a NH, and the only other possible proton that is likely to take is going to be one from one of these carbons down here. But I'm going to say right now that's probably not going to happen. So what we're going to do is we're going to say, okay, let's redraw this out to where now we have that NH bond there. And we're going to draw the acid-base reaction. So that's going to be our base is going to use its electrons to take that proton and give the electrons back to that nitrogen. And that's going to give us this structure here. Nitrogen with a negative charge. And we're going to have our NH2 now, right? Because the lone pair is forming a bond with the hydrogen. So now the nitrogen has another hydrogen attached to it. And then we have our spectator ion, which is that sodium just chilling out over here. Has nothing to do with anything. So now looking at this, we have our conjugate base as well as our conjugate acid. So we've done step one, which is predict the product. Next, what we have to do is we need to give a direction of equilibrium. So when we're thinking about giving a direction of equilibrium here, the acid is actually not in our pKa table. So we need to reason through this on where it would be. So looking at this, we can compare our two base stabilities, right? So looking at our bases, we are essentially asking which one is more stable. This NH minus versus this double bonded nitrogen. So we got to go through our effects, right? To remind you of what all the effects are, first off is size. Looking at these two atoms, they're both nitrogens. There's no difference in size. Second is electronegativity, right? We look at them, they're both nitrogens. There's no difference. Number three is resonance, right? Can we spread that negative charge out anywhere else? Well, the answer is no, because on the one with single bonds, there's no double bonds we can push around. And for the one that already has a double bond, there's no other pi bonds that we can move to help it out. So that moves us on to number four, which is induction. Well, they're only connected to carbons, so that isn't anything useful. Which brings us to number five, which is hybridization. Well, for this one, we do have a situation where these are different. right? The one on the left here is sp3 hybridized, right? Because remember that if it's just a negative charge, it's still sp3. It would have to have a pi bond to be sp2, and it can't do any resonance. The one over here on the right, on the other hand, it has a pi bond. That means it must be sp2 hybridized. And as we've seen in the past, if I draw a very small version of this diagram, and as we said in the last lecture, the closer to the nucleus is better. And so if we're asking which one's better in terms of being more stable, it would have to be the one that's sp2, right? Because closer is better. So that tells us that the conjugate base is more stable than the base, right? And if it's more stable, that means that the acid is more acidic than the conjugate acid in this case. So our equilibrium points to the right, right? It points away from the stronger acid. It points towards the more stable base. So we've done the first two things. We have determined the products, right? We've predicted them. We have determined the direction of equilibrium, and now we have to say why. And the why here is what we've already explained, right? Anytime you're giving a reason why, you can't just say because the pKa is lower, it's going to point away from that acid. You have to say why something would be like that. And the easiest way to say why is one of these things down in this corner, right? It is perfectly fine if you just write down the exact words that I put down there, but whichever one pertains to the particular situation. So if I were to give a reason why for this equilibrium, I can just say hybridization, and that is completely fair. I will understand what you mean if you say that. So, in conclusion, this is how you would normally work one of these out on a quiz or exam, right? You're going to go through, you're going to predict which is the acid, which is the base. You're going to figure out the products, find the equilibrium direction, and give one of those five effects as a reason as to why it points in that direction. All right, so let's move on to another one because I actually have 7 examples in total that I want to work through with everyone. So let's go ahead and do that with example number 2. So for example number 2, we're going to start with this here, and it's going to undergo a reaction with this here. All right, step 1, we have to predict what the products are going to be. I see a negative charge. A negative charge tells me that's probably a base, which means this other thing over here must be our acid. And thankfully for this acid, it's pretty simple to find the most acidic proton because it's only that carbon that has hydrogens attached to it, and they're all relatively the same. So, looking at what the products will be, the base is going to grab one of the protons from the acid, and it's going to give that carbon a lone pair with a negative charge. So there we go. Again, since the hydrogens are implied, I don't draw them in over here. I could, but I'm going to decide not to get everyone more used to bond line structure. So then we have our carbon that now has a lone pair and a negative charge. And so this is going to be our conjugate base. This is going to be our conjugate acid. Now for this one, it's pretty interesting because neither of the, or well, I guess the conjugate acid is actually in the pKa table. Once again, we have a situation where it kind of stinks because we don't have much information to go off of. So we're going to have to figure out our equilibrium on our own. And how we're going to do that is once again by comparing the base and the conjugate base. So looking at our base in this example, right, we have the negative charge on this carbon out here, which negative charges on carbons are a pretty bad thing. But the good news is at least it has some resonance, right? It can move that negative charge throughout that ring there. But the thing with this resonance is it can do quite a bit of it, but essentially in the end, all it can ever do is place negative charges onto other carbons. right? There's not really a time that it's ever going to put the negative charge anywhere that is significant in terms of being a better resonance structure, because remember, our re major resonance contributors are based a little bit off of electronegativity. Now we can compare this to our conjugate base, right? It's another carbon with a negative charge. But looking at this one, we can say, okay, we can do resonance here, break that triple bond, push the electrons up to the nitrogen. And this gives us a resonance form with a negative charge on a nitrogen. So these both do resonance. But as I said in the previous lecture video, one does better resonance, right? Because in terms of electronegativity, nitrogen is greater than carbon, right? And so since nitrogen is more electronegative, it is also better resonance. And better resonance is important because that essentially determines which one of these is going to be more acidic. And as a matter of fact, the better resonance means that this one is more stable. And so if the conjugate base is more stable, that means that the acid is more acidic, which means that equilibrium points to the right once again. And we have to give a reason here, right? Once again, we have to give a reason for everything. And it can be one word. In this case, we can say it is resonance. But for this one, resonance technically isn't enough, right? Because they can both do resonance. So we have to add a little plus here to say it's also due to the electronegativity in that resonance form, right? So this one is both resonance and electronegativity. So keep in mind that sometimes those factors matter together rather than just separate one at a time. All right, let's hop on to example 3. The same idea as all the others, right? The reason that I want to go ahead and give a lot of these examples is because I want to make sure everyone is comfortable with this material. So, looking at this one, this one's a little interesting because for example 3 here, we have two neutral species, which means that we don't really have a situation where we can immediately point out one is the acid or the base. So this brings up the example from the previous lecture where I said step 1 is you need to find the most acidic proton. The first things that you always want to be looking for is the atoms that protons are connected to. And so we see in the two different structures, one of them has a nitrogen, one of them has an oxygen that are both connected to protons, right? Everything else is just carbons. So we can kind of rule those out at the moment. So with that in mind, we then have to ask ourselves which is more acidic. And remembering from the previous video, electronegativity plays a big role in making things acidic or basic. And oxygen is more, oh, sorry about that, electronegative, and thus it has a more acidic proton. So if this is the more acidic proton, that means that this right here must be our acid, right? Which also means that over here has to be our base. And if you also remember from last lecture, we talked a lot about, or well, a little bit about how bases do have to have lone pairs. So it must be the nitrogen that's there that is actually our base. So if we redraw this alcohol group out, we can show that OH bond, and we can say, all right, the nitrogen's going to act as the base. It's going to use that lone pair to grab the proton, and then we're going to kick the electrons back to that oxygen. And so now we have this NH3 plus, and we make this O minus. And so this here is our conjugate acid. This here is our conjugate base. And looking at these, it's kind of tough to tell the stability between the two, right? Because our base and conjugate base, one of them has a negative charge, the other one is neutral. So it's very practical to say that, all right, equilibrium should lie in this direction, right? And the reason here is you can just say charge slash neutral, right? Because the starting materials are neutral. But here's the thing, right? We need to be careful whenever we think about neutrality. Because remember that whenever we were talking about HCl and water, it actually points towards the products which are charged. So it's not always true that neutral is better than charged. It depends on the strength of the acid. But in this case, we actually have some data that we can use to back this up, right? Where the acid here has a pKa of about 15, right? It's an alcohol. And the conjugate acid has a pKa of about 10. So indeed, we can say that the KEQ here is equal to the 10 to 10 minus 15, right? Because it's conjugate acid minus acid. So we do know in this case that the KEQ is 10 to the negative fifth, right? So we can confidently say that it points towards the left, and it is due to neutral charges. But this isn't always the case, right? We can take a look at example 4. Let's say we started out with something that looks a bit more like this. So once again, we have to do the same thing that we did last time. Find out what the acid is and what the base is, because neither of these have charges. Well, I will say that this proton right here is attached to an oxygen, and there's no other heteroatoms with attachments to protons, right? The nitrogen's not, other carbons are not. And looking at this, it's a carboxylic acid, right? We've seen these multiple times. That oxygen, once deprotonated, it'll have resonance that allows it to stabilize that charge really well. So this is an acid, right? That means that this other compound over here has to be the base. And as a matter of fact, it has lone pairs on that nitrogen that can act as a base. All right, so what we're going to see is this is going to come over here, deprotonate that alcohol, or sorry, the carboxylic acid. And that is going to give us the carboxylate we see here, as well as now that nitrogen is going to have a bond to that proton. Okay, so now we have our conjugate acid, or conjugate base and conjugate acid. And looking at these, your gut reaction, whenever you're looking at the equilibrium, is to point it to the left, right? Neutral is better than having charges. But again, not always. It really depends on how strong your acid is. Because looking at our acid, we have a pKa table that actually tells us that the pKa here is about 5. And then on our conjugate acid, we know that our pKa here is right around 10, because that is in our pKa table. So if you were to go through and actually calculate this KEQ, it's 10 to the 10 minus 5, and that KEQ is 10 to the fifth, right? Which, as we know, when a KEQ is greater than 1, products are favored. So charge neutrality does not always mean favorable. It often does, but it depends on the strength of your base and of your acid, right? And carboxylic acids are quite strong. They're right on that line of where it's a strong acid. And normally, when you're looking at things that are not, or that not being neutral is better, it's normally when things are a strong acid. All right, so our equilibrium in this case does point towards the products. The products are favored. And so with that, we have to say why. And the why here is it has to do with the stability of our conjugate base. And we've already talked multiple times about why this is stable. It has to do with both electronegativity and resonance, right? Because the electronegative oxygen's happy with the negative charge, and the resonance shares the negative charge between two oxygens, which is a good thing. So overall, that's what we're looking at for this example here. Charges are not always unfavorable. It really depends. Let's move on to example 5. All right. For example 5, let's say we were given this structure here and this alcohol. Oh, sorry, I almost started drawing out the products. So we have to predict the product of this reaction. And we see a negative charge. Negative charge tells us this is a base. That tells us that this must be an acid, and it does have that OH, which is an acidic proton. So our base can come over, grab that proton, toss the electrons back to the oxygen. We end up with this here alongside the negatively charged oxygen here. So this is our conjugate base, and here is our conjugate acid. And so looking at this, we once again, we can compare these via the pKa table, but we're not going to because this one is very obvious, right? Looking at the differences between the base and the conjugate base, they both are negatively charged oxygen, so size and electronegativity is the same. But then in terms of resonance, the starting material, the base, it has resonance with both of these oxygens here, right? It can put the negative charge on either of those, whereas the conjugate base can't. So simply stated, the base is very stable, right? And so our equilibrium is going to point in that direction due to resonance. All right. Some of these are very easy to do. That's why I tossed this one in the middle. Some are a little bit harder. Let's take a look at another example. This will be example 6. So for example 6, we're going to toss in something a little interesting. We're going to do this here, and we're going to do an alcohol. So once again, we have stuff that is not charged. And so what we have to do is we need to ask ourselves, all right, which is going to be the most acidic proton, right? Because that's going to help us determine the acid. And looking over here at the compound on the left, it's just a bunch of carbons, right, with a bunch of different bonds to them. But the compound on the right conveniently has an OH. So this right here is our most acidic proton. And so that would tell us that we should probably call this the acid. But there's one problem. If you look at the compound on the left, it's all just carbons, right? There are no lone pairs. And what that tells us is if there's no lone pairs, this can't be a base. This is an exception to something that we normally see because for all these other reactions, we've been looking at things that once you identify the most acidic proton, normally it's just a hole in one. You see the other thing, it has to be the base, and then you find out where the basic electrons are. In this case, that's not true. Right here, we're looking at it, and since this has no lone pairs, it can't be a base. That means that this is not even the acid. This is actually the acid. The alcohol, the oxygen over here, has lone pairs, which means this is actually the base. So we don't even care about this acidic proton. It is not useful to us. We don't care about it. We have to find the most acidic proton now on the compound on the left. And so looking over here, if we have carbons, remember most everything's crossed off the list but hybridization. And so looking right here on the end, this is an sp hybridized carbon. So it must be that proton there. If we were to draw the products here, right, we could deprotonate that structure in that spot. So that would give us a carbon with a negative charge. And it gives us this OH2 plus. This one shouldn't be too hard for everyone to figure out. We know, based on the line that we've seen before, that this conjugate acid, being a positively charged oxygen, is a strong acid. And as we saw over there, it's not like anything over there was very strong. And so what that means is our equilibrium is pointed to the left. And if we had to give a reason as to why, it's because we're making charged stuff on the right-hand side that's super unstable compared to the stuff on the left. So this is due to charge neutrality, right? Charge slash neutral. All right. We're gonna do two more examples. I'm gonna give you another freebie just to continue down the line because I do think this is useful information. So let's do example 7. So for this one, we're gonna have this phosphorus here, positively charged, and then we'll use NH3. Here we go. So for this one, normally, whenever we're looking at reactions, we like to talk a lot about having things that are negatively charged be bases, but remember that we can use the opposite to say that things with positive charges are usually acids, right? At the same time, we have this NH3 here, which must be our base, and it does indeed have a lone pair to do so. So, looking at that, the nitrogen come over here, grab the proton, give the electrons back to the phosphorus. So now the phosphorus is hanging out with a lone pair on it. And we have NH4 plus. And so now we have our conjugate acid and our conjugate base. But the thing is, we don't have pKa values for the acid. So we kind of have to figure out exactly what is going on. And this is where we run into an interesting dilemma, right? Because what we're essentially comparing is if we're comparing the base and the conjugate base, we're pretty much comparing. I'll abbreviate this as ET. That just means ethyl, right? Because those are ethyl chains hanging off of the phosphorus. But if you're comparing these, there's nothing to compare in terms of stability. They're both neutral, and so it's kind of a big question mark, right? For acid-base chemistry, every time we've been comparing these conjugate bases, they've generally been negatively charged. But this is a case where that's not true. And this is actually a case when we have to look at something different, right? Because even though we like to look at conjugate bases, I have one recommendation that'll help you out a lot. All right, and that is always look at the unstable thing, right? And so if you're looking at the unstable thing, in this case, it's the acids, right? Because the acids are the things with the positive charge. And if we're looking at the acids in this case, it makes our life really quite easy because we can use the same factors of acidity to determine when something is more acidic, right? And the first one of those is size. And we know that phosphorus is bigger than nitrogen. And as we said with size before, bigger is better and more acidic. So in this case, it actually helps us out knowing that phosphorus is larger in terms of size because that tells us that this acid over here must be more acidic. And it's not necessarily due to the stability of the conjugate base. It is due to the instability of the acid itself. And so that tells us our equilibrium direction, right? Because it points away from the more acidic acid. And the reason in this case is, like we just described, due to the size. So if you have things with positive charges, start to think about which one is going to be more acidic and why. It's the exact same reasoning, it's just thinking about it in a slightly different way. All right, we got one more because I said I was going to give you an eighth example, even though I was only going to give you 7. And we're going to do this here. Sorry, I should probably do this. Okay. All right. So for this structure down here, first thing that I see, K, that is potassium, right? And potassium isn't going to matter to us. It's just a spectator. Because this is an O minus, it's K plus, right? And as we talked about previously, this is just a spectator ion. Where we see that negative charge, we know this is a base, which means that this over here is our acid. But looking at acidic protons, we don't have any attached to the oxygen, so it must be one attached to the carbons. We have protons over here. We have some in the middle. We have some over here. The question becomes which one's going to be the most acidic. And I'll tell you right now that it's going to be in the one in the middle. And the reason it's going to be that one in the middle is because upon deprotonation, you can do resonance with two oxygens. So, looking at what this reaction is going to look like, the electrons from our base can come over here, grab that proton, and we can put a negative charge on that carbon. So that gives us our carboxylic acid. That gives us our negatively charged carbon. And we have that potassium that stuck around. Right? And so looking at the difference between these two, right, we have this is our conjugate acid, this is our conjugate base. If we're comparing our conjugate base and our base, we see that for the conjugate base over here, we can draw some resonance forms, right, where from an orange, we can move the electrons up to the oxygens, right? And so we have this one here, and we also have another one. I'm not going to draw the electron movement for it, but it's this here. Versus in our starting material, oops, we end up with this one here. And so in both cases, we have resonance between two oxygens, right? Because over here, this is just two oxygens sharing the charge. Over here, it is two oxygens plus a carbon sharing the charge. And so you may think to yourself, wow, it sounds pretty good to have the extra carbon in there to share charge. But the one important thing to keep in mind is you're still deprotonating a carbon. You are still leaving a carbon with a negative charge, right? That is the first place that it sits. And that is bad, right? Anytime you put a carbon with a negative charge, it is generally a bad idea. And this case is not that much different, especially when you compare it to something that shares with two oxygens and it already has a negative charge on an oxygen, right? And so because of that, we can say that the equilibrium is going to point this way due to electronegativity, right? Because we start out where a negative charge is on a carbon versus a negative charge on an oxygen, we'd rather have it on the oxygen. And so this right here may seem like a little bit of a stretch, but we do have a reasonable way to explain this as well in terms of pKa, because looking at the acid, this is actually in your pKa table, right? It has a pKa of about 10. Whereas the conjugate acid, the carboxylic acid itself, has a pKa of about 5. So our KEQ for this overall reaction is 10 to the negative fifth, right? So it does point towards reactants. And so this is an example of one that I wouldn't expect you to immediately know that the carboxylic acid is more acidic, but it helps to know those pKa's. All right. So from this lecture, hopefully you were able to gather knowing the pKa's can be useful in some situations, right? It can give you an idea for something like this, where it's like, I don't know which one would actually make more sense. It gives you an idea of which would be more acidic. For something like this one up here, where for an interesting reason, the charged species are more stable, right? It helps you understand that. But then there are other times that you don't know them, and you kind of have to go through and determine on your own which way the equilibrium is going to lie, right? You don't want to use pKa's as a crutch. You want to use them as an assistive tool in understanding acid-base chemistry. But overall, start preparing yourself for these types of questions on exams. They will be on your practice worksheets, as well as we will continue to present them as we go along. Next time, we'll talk about Lewis acid-base chemistry, and that will close out acid-base chemistry as we start to lean into the final bits and pieces before we get to exam one. We'll see you next time.